Does this work? Okay. Okay. Thank you, sir, for the introduction. It is great to be back here where I spent 5 years studying physics. And I'm very grateful for the opportunity to present my research here today. So I'll be talking about gravitational wave astronomy, but in the particular context of this new regime of foundational AI. And I aim to give you a brief overview of what the field of foundational AI is all about and how some of the challenges of modern gravitational wave astronomy can potentially be tackled using foundational AI. So, like Sir mentioned, I live in Nashville, Tennessee, and this is a picture of the Vanderbilt University campus. And the great thing about being in Vanderbilt or in Nashville is that we not only have Nashville hot chicken and Taylor Swift, but we also have a lot of gravitational wave astronomy that we can do. So I am personally involved with just the LIGO-Virgo-Kagra collaboration, and I look at binaries which are around stellar a few times to a few hundred times mass of the sun, which are detected by the ground-based gravitational wave interferometrics, LIGO-Virgo and Kagra. But others in Vanderbilt are also involved with the Space Gravitational Wave Telescope called LISA. And then there's another group who is looking at gravitational waves from pulsar timing array, which is gravitational waves from supermassive black hole mergers. And they are part of the nanograph collaboration. So I collaborate with Professor Karan Jani. He is here in the middle. And this picture was taken right after I had joined Vanderbilt. So we have a few new members who are not there in this picture, but there are members of from different disciplines because Vanderbilt happens to be a very interdisciplinary institute. So we have students from data science, computer science, engineering who are also involved in this science.
You can take this chair. And Chayan, you can
Yes.
use this.
Oh,
Will not move the slides, but you can point. I can show the
okay. So I like to show this picture because it basically gives an idea about the breadth of gravitational wave research that happens in the department. So I work in this regime, which is ground-based gravitational wave detectors with Professor Karan Jani, but there's also millihertz gravitational wave, which can be detected using LISA, and then nanohertz gravitational wave is detected using pulsar timing, and Professor Steve Taylor is leading that group. But also there's Professor Mallory Molina, who joined very recently in our department, who works on black holes in dwarf galaxies, and Professor Jesse Rano works on quasars and HALs. Right. So today's talk, the title consists of two parts, gravitational wave astronomy and foundational AI. I'm assuming that people will already be a bit more familiar with gravitational wave astronomy as compared to foundational AI. So I'll give a very brief introduction to what it is all about. So gravitational waves are ripples in the fabric of space-time. They are ripples in space-time curvature, which are produced by these heavy compact objects, which are two black holes orbiting each other. And when they orbit each other, they produce these perturbations which propagate at the speed of light. These are called gravitational waves. And using these instruments, these ground-based instruments like Hanford, like Livingston and Virgo, we are able to see only the final few seconds of this in-spiral and merger phase of the evolution. But these black holes orbit each other for hundreds of millions of years. Now, what is foundational AI? So to explain this, I'll begin with a little story. So in 2018, 2019, there's this big company called OpenAI, and they decided to train a new kind of neural network. It's called Generative Pre-trained Transformer, or GPT. Now, they decided to do something unusual. So usually in machine learning, if you want to train a neural network, what you do is you have training data. Let's say you want to classify between images of cats and dogs. What you would do is you would maybe write your favorite machine learning model, add a bunch of neural network layers, and then you have to provide the model millions of pictures of images of cats and dogs for the model to be able to distinguish between them. But what they decided was, how about we don't provide any label to the neural network. Let's just feed in the data in a very task agnostic way. So you're not training the model to do a specific task, rather, you're training the model to learn the data itself. So they did this by first taking a look at text data. And what they did was they took a bunch of sentences and then they removed a few words from the sentence and they asked the neural network to predict the missing word. So this is called self-supervised learning. And what they found was that this gave them much better accuracy at text prediction than some of the other text-based models, which was used prior to that. So that became GPT-1. This was 2018, 2019. Then in 2020s came GPT-2. In 2022, there was GPT-3. And all of them were improvements over the GPT-1 model, but still they didn't get as popular as later. So what happened in 2023 onwards is they released GPT 3.5, where they added human in the loop intervention, which means the outputs of the neural network were not only being produced by the model itself, but there was human in the loop who was giving feedback to the neural network. And so by using this human intervention, by using human in the loop feedback approach, their model became much more powerful, and then decided, and then the people who were the CEOs of OpenAI and the other people, they decided how to make billions of dollars out of this extremely powerful tool. So they created a chatbot, which we now know as ChatGPT. So the reason I say this story is because GPT is a foundational model. And the reason we call it a foundational model is because it was not trained to do any particular task. Rather, it was trained agnostically to learn the data, and then you could tune the model to do any task that you want. ChatGPT can be used to do any, so you can build a chatbot out of it, you can translate from one language to other, you can do n number of things. Wherever language is involved, you can use this model. So that is the idea of foundational approach. Oh, sorry. So the field of machine learning has moved from just standard standalone architectures to foundation models, which is one specific model which can be adapted for multiple tasks. And the idea is you can pre-train these highly flexible models on general tasks using self-supervised learning, which I mentioned, on very extremely large data sets. And then you can adapt these pre-trained models to perform various tasks without additional training. So this is known as amortization. It means you pay the price once, you train a very expensive model on large data sets once, and then you can do millions of different tasks without having to retrain the model again and again. So in this talk, I'm going to try and motivate that there is a case to build a foundation model similar to a ChatGPT for gravitational waves. And so disclaimer is I have not built a foundation model, and I have not completely solved all the problems of gravitational wave astronomy using my ChatGPT for gravitational waves. Rather, I'm going to motivate the case for why such a model could be useful, and we'll see how we can build one.
Is generative AI and foundational AI same, or?
No, there is slight difference, because generative AI is any model that can generate new samples. For example, you have noise and you can generate a new image out of it. That is a generative model. That will give you new samples. That is a generative model. Foundation model is a more general idea where you are basically using self-supervised learning. You're training the model in a task agnostic way. That gives you a foundation model. Any other questions? Okay. So my question here in front of the audience is, can foundation AI help address some of the major challenges we face today in gravitational wave and multi-messenger astronomy? For that, I'll first talk about some of the current challenges that we face and how individual machine learning model is being used to tackle some of these challenges. Because when I joined LIGO, it was in 2019, and the field of both applications of machine learning in LIGO as well as the field of machine learning in general was very different than what it is currently. So since then, machine learning has become much more prevalent within LIGO. But now we have even more modern and more sophisticated tools. So we'll first look at how the field of machine learning applications in gravitational wave has progressed, and then I'll introduce foundation AI for gravitational waves. So first I'll talk about gravitational wave searches. So I mentioned about the LIGO detectors. So they are recording the data all the time. But the task that we need to do is we need to find those very faint astrophysical signals in the noisy data. So there are two ways to do this. One is model search. Here we do something called mass filtering, which means we have the data here and we have a template. So this is a simulation of what the gravitational wave signal will look like depending on masses and spins. And then we cross-correlate the data with the template. And if there is a match between the data and the template, as we can see here in this example, we get a very loud output. It is known as the signal to noise ratio time series. So depending on the loudness of this signal to noise ratio, as well as some other metrics like chi-square and other tests, we determine whether there is an actual astrophysical signal in the data or there is noise. So this is a modeled approach because we are modeling these template bands. The other approach is an unmodeled search, which is based on coherent excess power. So remember, there are three detectors, LIGO Hanford and LIGO Livingston, and then we have Virgo. And in this method, we look for coherent excess power in the data, which are within, let's say, 10 milliseconds of each other, because the light travel time between Hanford and Livingston is maximum light time delay is 10 milliseconds. So if there is a excess power in that within that 10 millisecond window, then it is a gravitational wave candidate. Now, as you might imagine, doing this for millions of, we have millions of templates of these gravitational wave signals, and doing this millions of times is obviously very expensive. And when we have high detection rates, for example, in O4, we have a few detections every week. In O5, we'll have multiple detections every day. So methods like this are extremely computationally intensive, and it is not going to be feasible.
So Chayan,
yes.
You say that you have multiple templates.
Yes.
Do you mean to say these are like many other models other than GR, or like why? What is the difference between these templates?
The masses and spins.
Oh, so the parameters.
Yeah, it's just the parameters. But there are.
So you are not.
Yeah.
Okay, so you do have a number of waveforms.
Yeah.
Based on mass and spin.
Just mass and spin.
And then you just fit or extrapolate or whatever to find out that what is the mass and spin of the.
That is for online detection. So there is a critical difference here. For online, we need quick search.
Yes.
But for offline, we'll have more expensive waveforms which have higher order modes, which are more optimized for, let's say, intermediate mass black holes. So these do not have all the physics in them.
Oh, so that means this is not like you have a waveform and you critically fit it to a theory. You just match.
This is just match fit. Exactly. Right. Now, the idea of doing searches for gravitational waves is a bit convoluted. So, for example, I mentioned about that, classifying between cats and dogs. It's not as straightforward as outputting a probability of whether a given data contains a signal or not. The metric that LIGO really cares about is called a false alarm rate. What it means is that what is the probability that the model will produce an output which is as high as from the background data where there is no gravitational wave as the one it produces in the foreground data which has a gravitational wave. So the output of the pipeline is a ranking statistic. For mass filtering search, the ranking statistic is the SNR. And we run this pipeline, we run the mass filtering algorithm over data where there's no gravitational wave. And we build a distribution like this. This is called a background distribution. And then we count how many triggers in the background distribution are above a certain threshold. And we select this threshold based on how the pipeline has been optimized and all of that. And the number of triggers which are above this threshold quantify the false alarm rate. So if I have, let's say, 1 month data, and I have 10 triggers which are above this threshold, the false alarm rate would be 10 per month. It's like that. So for any gravitational wave to be detected in the online detection method, it has to have a false alarm rate of less than 1 per month. Usually 1 per 2 months is the criteria for O4. So this is the kind of computation that we need to do using any search method, whether it's a machine learning method, whether it's a match filtering method, we need to do this computation. Yes.
How do you set the threshold? Because there is nothing to match with or something like that.
So we do this using injections. So we generate a lot of fake data. Before the start of the O4 run or any visual run, we generate a lot of fake data. We generate injections. We look at.
So you don't have any signal there. It has only the noise.
So we also run this on foreground data where we have injections. So we have gravitational waves, and we look at the distribution of the foreground ranking statistics and the distribution of the background, and we optimize the false alarm rate. Like what threshold should I set to have the false alarm rate of at least 1 per month, as well as get the number of all the injections which are in the foreground data. Okay, now gravitational wave searches using machine learning has also progressed quite a bit. So here we had the first machine learning mock data challenge for gravitational wave searches. This was back in 2022-2023. Here several machine learning pipelines participated in this challenge, along with one match filtering pipeline, which is PyCBC, and CWB, which is the unmodeled pipeline, which looks at excess coherent, excess power. And here these plots show the false alarm rate versus the sensitive distance. And sensitive distance is basically a measure of how far you can look at a binary, a black hole merger, with a signal to noise ratio of 8. So we can see here that there were 4 data sets, which was part of the mock data challenge. And out of these 4 data sets, data set 1, 2, and 3 were gravitational wave injections in Gaussian noise. And Gaussian noise is like very standard with non-stationary. So it's not very complicated. But data set 4 had gravitational wave injections in real LIGO noise. And the thing about real LIGO noise is that it is non-stationary and it has very sharp noise artifacts called glitches. I'm going to talk more about them in a minute. But the takeaway from this figure is that if you look at the false alarm rate of 1 per month, which is this very last point, you can see that for Gaussian noise, machine learning pipelines do perform, at least some machine learning pipelines have a similar performance to match filtering, but most of the machine learning pipelines fail when there is real LIGO noise, because the noise is non-stationary and they contain glitches.
Sorry, sorry for I didn't get it.
Yeah.
So you have 4 data sets.
Yes.
And what are the difference between the left-hand panel and the right-hand panel?
So this is a different. So I'm only talking about the mock data challenge right now. So just
okay. So you have 4 data sets.
Yes, 4 data sets.
All of these are mock data sets.
These are all mock data sets.
What is the difference between the 4?
So data set 1, 2, and 3, the noise, Gaussian noise.
4 has real LIGO noise.
4 has real LIGO noise.
Right. And what are these 4 colors?
These are the different pipelines. So for example, MFCNN, CNN Coin, TPI FSU, and Virgo, AUTH, these were machine learning pipelines. PyCBC is a match filtering pipeline, and CWB was a unmodeled excess power pipeline.
Okay.
So the blue one, the blue kind of part.
The blue, this one is MFC. This is also a machine learning pipeline, CNN based machine learning pipeline.
And so what is the takeaway?
So the takeaway is that at a false alarm rate of 1 per month, which is if you look at this, there are some machine learning models which have comparable performance to match filtering and other standard searches. But for real noise, almost all of them fail. They do not live up to the sensitivity of match filtering or unmodeled searches, standard searches. But there are other machine learning models. So A-Frame is a very new pipeline which is currently operational within LIGO. And they have improved upon these machine learning pipelines. And you can see that for certain masses, for example, M135 and M235 solar mass, they can outperform match filtering, even in real LIGO noise. But for lower masses, they still struggle. You can see the sensitivity of these searches have dropped for low masses. So the takeaway from this slide is that machine learning models can show comparable performance to match filtering in Gaussian noise, but they usually struggle a lot when there are signals in real LIGO noise, which has a lot of non-stationary transient features. And there are recent approaches like A-frame, which actually demonstrates comparable performance to match filtering even in real LIGO noise, but usually in higher mass ranges. But it's struggled.
And
Yeah.
the reason for that is that because they do not have enough training set, or what is the reason for not performing,
Yeah.
performing much worse
Yeah.
than the match filtering?
So one reason could be the signal itself is quite much long if you have smaller chert masses. So when you have longer signals, an SNR10 signal, the SNR is distributed over a longer waveform. So the overall SNR in the last few seconds is much less for a longer signal compared to if you have a shorter signal. So that is one systematic challenge.
Okay, but no, my point is that
Yeah.
we see that match filtering is definitely doing well.
Yes.
But it's computationally intensive, and we
Right.
just want to go to ML-based
Right.
approaches to to make our things faster, much faster.
Right.
But as you showed us that
Yeah.
ML approaches are not doing well
Right.
when it comes to real life
Oh,
noise. So my
so
question is
why is the real
what,
life?
what
Oh,
is
okay.
the thing
Yeah.
not doing well in the real life?
In real life.
And which compared to when it's Gaussian, it's performance.
I have a few slides like just after this. So
Sorry.
sure, no problem. Okay. The other major analysis that we do within LIGO is parameter estimation, where we try to estimate the distribution of the parameters of the binary black holes which are producing the gravitational wave. For example, the masses, the spins, the sky direction, etc. And usually we do this using Bayesian inference, where we solve for the Bayes theorem, which is we try to estimate the posterior distribution of the system parameters theta, given the gravitational wave strain data S. And for this, we need the likelihood distribution, which is based on the assumption of stationary Gaussian noise. So when we do MCMC, or when we do standard Bayesian inference, we need a likelihood function, and we assume that the likelihood is stationary Gaussian, which is actually not true. This is the probability of the data given the system parameters, and this particular assumption of stationary Gaussian noise, it works for parameter estimation because usually the data can be assumed to be Gaussian for, let's say, if you consider just a few seconds of data, we can approximately consider it to be Gaussian. The other parameter which is important here is a prior, which is based on our beliefs about the system parameters before looking at the data. So we have some kind of assumption from astrophysics about what the range of masses of black holes are going to be, and all of that is encoded in the prior distribution here. Now, the challenge of parameter estimation is that we not only want to just write down a posterior distribution. We cannot do that because it is an intractable problem, because this is a 15-dimensional parameter space that we are probing for gravitational waves. There are 15 parameters that describe a gravitational wave signal. So we need some approximate methods, and usually we use iterative samplers like Markov chain Monte Carlo or nested sampling, which involves a random walker moving around in parameter space, drawing samples, and then based on acceptance or rejection criteria, some samples are accepted, some are rejected, and ultimately these MCMC chains, they build up a distribution that looks like this. Here is an example distribution of the primary and secondary masses of a gravitational wave event. Now the problem here is that we need to evaluate the likelihood function several times, thousands to millions of times, when we are doing parameter estimation. And all of this involves computationally expensive waveform generation and noise-weighted inner products. So this will take a really long time. With standard nested sampling, for example, a binary neutron star merger, if you want to get the full 17-dimensional parameter estimation for that event, it will take you several days to even a few weeks. And also there is another problem with these sampling-based techniques, which is if you have disconnected posterior modes, the walker can get stuck in a low probability area, and it is not easy for for the sampler to jump from these disconnected modes. So the sampler can just get stuck in a low probability posterior mode. So that is another issue as well. So the method which has become really popular within LIGO is to use a surrogate model for the posterior using a neural network called normalizing flow. And this was actually the main focus of my PhD, to build normalizing flow models for gravitational wave sky localization. So I try to estimate the sky location parameters of gravitational waves using normalizing flows. And the way it works can be explained using these animations. So first I'll talk about normal MCMC, where you can see these are two disconnected posterior modes, and you have this random walker which is moving around in parameter space. And because this walker employs this local kernel here, it is usually difficult to move from one part of the parameter space to another. It is not easy for it to jump from one posterior mode to another, and can get stuck in one of the modes, and they won't be able to sample from this mode at all. However, this normalizing flow is a very different technique. And the way you can think about normalizing flows is like modeling something out of clay. So let's say if you have a lump of clay, and then you apply some perturbation, you drag and you push and shove, and you do some sort of modification on the clay to make a beautiful sculpture. Normalizing flows work in exactly the same way. You start with a simple distribution like a Gaussian, and then you push and pull at those Gaussian samples, and you create the distribution that you are trying to estimate. So here in this, yeah.
Sorry.
Yeah.
Sorry. Can I think of your normalizing flow as something where you are adapting the prior? So it's like adaptive prior kind of approach because suppose in a normal
That is very
case
true.
you have a prior,
Yeah.
and you're stuck with the prior, and
Yeah.
that determines your distribution space and
Yes.
everything, and your posterior could be heavily influenced by that.
Exactly.
But does it here in the normalizing flow, does it mean that based on the geometry of your three-dimensional parameter space, you are actually kind of normalizing your prior or adapting your prior something?
That is very true. So you can think of it in terms of Bayes theorem as well. So the simple distribution that we start with is a Gaussian, it can be your prior. And then you have a neural network which is predicting how to map that prior into the posterior.
Okay.
So all of this modification that I was talking about, this tugging and pushing and pulling at the Gaussian samples,
the neural network.
This is the neural network is predicting it, and it does this extremely fast. So for example, if this takes you an entire day to estimate, then this will take you less than a millisecond. So and now this is a generative model. So it can generate new samples from the posterior, and it can also evaluate the PDF, the posterior density function, at new locations after the model has been sufficiently trained.
It's in what data?
Over the strain data. So given the gravitational wave data, the neural network will input the gravitational wave data, and it will learn the transformations that it needs to do on the Gaussian samples to estimate the complex distribution that we are trying to estimate.
But the template it is means the parameter it is estimating.
Yes.
That should give us some kind of template or something.
Yes. So exactly. So when we generate the training data, we have a bunch of templates. That is, let's say, our prior distribution. We generate our training data, which is the gravitational wave signals based on those parameters. And then we train the normalizing flow using that gravitational wave data that we generated using those chosen prior samples. And then the neural network is learning for this particular gravitational wave signal. This is how I need to modify my Gaussian to produce the posterior distribution that we chose. Yeah.
It's continuous Bayes theorem.
Yes, exactly. Yeah. So one of the main focus of my PhD and one of the projects that I really enjoyed doing was pre-merger sky localization of binary neutron stars using a normalizing flow method. So why is pre-merger localization important? So studies have shown that binary neutron stars will spend 10 to 15 minutes in the advanced LIGO and Virgo detector band at design sensitivity, and 7% of the total detectable events will be detected 60 seconds before merger, and about 49% will be detected 10 seconds before merger. And among them, 2% will also be localized to within 100 square degrees of the sky. This is of course important for electromagnetic counterpulse because BNS mergers are they are followed by short gamma reburst, kilonova, and afterglow. And we really need to capture the short gamma reburst within a few seconds after the merger. But because the kilonova and afterglow, they persist for some time. So we need to be able to detect and localize these events before they have merged. And studies have shown that at advanced sensitivities, a certain fraction of these samples can actually be detected and localized to within reasonable sky areas. So I built this neural network, normalizing flow-based neural network called GW Sky Locator. And the special feature about it is that instead of training it on the waveforms, as you mentioned, it is being trained on SNR time series. So I'm feeding the network the outputs of match filtering pipelines. And this is mainly because I worked in a group which ran one of the match filtering pipelines in LIGO. So I could directly feed in the SNR time series from the match filtering pipeline that we ran. And I also used the intrinsic parameters of the templates, which was used to generate the SNR time series. And I trained this neural network model to estimate the sky areas. And here is an animation that shows how the sky localization area improves from 60 seconds before merger to 0 seconds, which is at merger, for a simulated binary neutron star event. So yeah, so this was one of the main projects.
I mean, why would you think so? Because
SNR.
of electromagnetic
No, the SNR. You're getting more and more signal. So the pipeline that I developed was meant to be run in a match filtering setup. Yes.
So you were talking about sky localization.
Yes.
So you need 2 or 3 more data. So how many?
Yeah.
How many?
So here I had Hanford, Livingston, and Virgo, all three. Yes. Yeah. But we can do 2 detectors as well. With 1 detector, you cannot do any localization. So the GW Sky Locator was meant to be run in a match filtering pipeline, but there is this new model called Dingo, which is an end-to-end machine learning pipeline. It runs directly on the strain data, the strain gravitational wave data, not on match filtering outputs. And it is also based on normalizing flow, but it also does some important sampling on top of it to improve over the normalizing flow outputs. So the normalizing flow generates an approximate posterior, and then they do important sampling to improve over it. And on the left is the result. This is a corner plot of the parameters estimated by Dingo for 150914, the first binary black hole event detected. And this is 170970, the first binary neutron star event which was detected. And if you squint really hard, you might be able to also make out that there is MCMC posteriors here as well. So this basically shows that using normalizing flows, these are so flexible models, you can actually get posteriors which are almost indistinguishable from full MCMC or nested sampling at within milliseconds. So that is how flexible and how powerful these models, generative models, are.
How many parameters you are getting out of it?
So all of them. So for this was 15 dimension. Here, not all of them are shown here, but Dingo can do full 15 dimension parameter estimation of all.
That's within milliseconds.
With yeah. Now, to answer SMM's question, why does machine learning fail in real noise scenarios, right? So this is what we expect from a gravitational wave signal. Extremely clear signal. So this is 150914, the very first event we detected. Extremely clear signal, of course, very bright. But in reality, this is what we see. So we have a signal here, but here we have things called glitches. So glitches are non-stationary noise transients, which are coming from various sources. Some of the sources have been identified. We know why these glitches occur, but some of the sources are completely unknown. And there is a particular kind of glitch called blip glitch, which occurs once every minute in LIGO, in 04. And the other trouble is that these glitches new kinds of glitches are coming up all the time. We see new glitches all the time in LIGO. And even the glitches which are identified, they change their morphology all the time as well.
Is the source of these glitches, I mean, detector noise or just...
Yeah, mostly. For example, one of the most troublesome is called scattered light, which is basically light scattering off of the mirrors of LIGO.
And that has not been controlled. What is surprising is that they change their morphology. I mean, even if you characterize them.
Yeah, because sometimes you have commissioning breaks. Even within a LIGO run, you have commissioning breaks. The detectors have improved. There has been some changes in the detector, and then everything about the glitches has changed.
But if you do the cross correlation between two arrays, those should be eliminated.
Yes, so that is why match filtering usually does better. But if you have a CNN, a convolutional neural network, if it looks for excess power, it might see an excess
If you are
power.
operating on only one detector.
Yes. For two detectors, sometimes, you can check, it forms as a check and balance. But for single detector, obviously, we have so much glitches, we really lose a lot
But
of.
for sky localization, you have to have.
We have to.
So then the cross correlation, we should remove those pieces as well.
Yes, but it still affects, for example, if you are running MCMC or nested sampling and the data has a glitch and you haven't subtracted it, it will affect your parameter estimation.
If I haven't subtracted it, it should.
Yes, and I have an example here, but
It should. I am not asking. But if you are doing it, then you should be able to remove it.
So I think the point is that if you have two detectors,
Mhm.
then the glitches should be removed. And
The gli-
why is that not so easy? I mean, maybe that's the question. Our just basic sense says that since these are glitches in detectors,
right.
so if you look at two detectors,
For detection, it might be fine, but the main trouble is inference for parameter estimation.
I see.
In any case, parameter estimation, you do it not online afterwards, most of the cases.
For BNS, we need it. For example, for 17.17, there was a huge glitch in Livingston, and we had to remove it all in real time to get the electromagnetic counterparts. So for BNS, that is
for these issues that once you detect, you need localization, you need electromagnetic
for
counterparts.
BNS, it is a.
So that's what I'm saying. The moment you are trying for localization, you should use two.
No, but the point is that it's understood that cross correlation will remove, but if you, let's say there is this blip glitch that is coming every minute, so then there is some other glitch in the other detector, then that can coincide with one of these blip glitches, and then you will find a signal.
I mean,
So
not
I mean, if
rare
there are too
glitches.
many glitches, then even cross correlation will find
Yeah.
some common
I think
glitches.
all our hard work will go in understanding what are glitches.
Exactly, because
That's true. That's true.
all the downstream analysis that we do in LIGO is dependent on the data, and this is what the data looks like. So it's a big problem. It's a very fundamental problem within LIGO. And give an example of the kind of inference challenges that we have if we have glitches. There was this event GW200129. It was a Nature paper, and it showed the first evidence of spin precession. So this is the unmitigated. So in purple, you can see the unmitigated postulator of chi-p. Chi-p is basically a spin parameter, which is the precession, measuring precession. And you can see that there was a glitch in Livingston during this event. And if you look at some of the glitch subtraction models, once you subtract the glitch out, the chi-p is completely uninformed now. So the entire parameter estimation is biased if you have glitches. Depending on the glitch subtraction model you use as well, our parameter estimates get biased.
So I guess the Nature paper was not retracted. I mean,
It's still there, but there were many follow-up papers challenging. This is one of them. All right. So we really have to do a lot more on detector characterization and understanding glitches, but right now we have a machine learning pipeline called Gravity Spy, which is running. And the unique thing about Gravity Spy is that it is a citizen science project. So anyone can go online to the Gravity Spy website and identify glitches and classify into different groups. And even within LIGO, you have Gravity Spy running, and you have also human in the loop intervention. So there's a lot of human vetting involved in within the Gravity Spy setup. But we want to automate all of this. We want more powerful models, computer vision models, which are much better than humans at classifying these kinds of glitches. So I mentioned about the general problems, but now I want to come back to the more recent times where we had GWTC4 and the data was released from the first half of the fourth observing run. And we had many exceptional events from this first half of fourth observing run. And I'm going to talk about a few of them, and I have placed a star at the names of a few of the events, and which I believe personally is an interesting candidate for a foundational tool. So first I'll talk about 230529. It was likely the first NSBH event of '04. And the reason it is an exceptional event is because the primary lies in the lower mass gap. Which is between 3 to 5 solar masses. So although there's a more likely chance that it is an NSBH, but still, since this is the first event that we observed where one of the components lies in the lower mass gap, it is considered a special event. And it's also the most symmetric NSBH that we have seen so far. So this is M1 and M2. You can see this is the 230529 and all the other NSBH or PNS mergers that we have seen in LIGO so far. The second exceptional event, 230814, and this is one where I feel Foundation AI could be useful, is a very loud event. It is a single detector event with an SNR of 42. And it is the first confident detection of L equals M equals 4 mode. So we detected the higher order mode in the inspiral with a very high confidence for this event. And the reason it is also interesting is because there are some deviations from general relativity which has been observed for this event. So here is the data, and you can see in the first 4 panels, the data is being fitted with a GR waveform, which means these templates have been generated using GR. And the other one is a non-GR waveform. Now, I don't know the details of all the non-GR physics that went into it, but it appeared that the data seems to be matching much better with the non-GR waveform than the GR waveform, especially this particular mode is fitting well with the non-GR waveform rather than the GR one. Although the paper also says that such deviations, minor deviations from GR in the ring down phase are likely due to non-stationary noise features, but it's still interesting.
So the first 4 you said are GR.
Yes.
What is the difference between all the 4?
So if you look at just this peak, I don't think it is very visible here. So the data, so for example, the
I
amplitude
think
sort
he's
of,
asking that what are the within the
right. Higher order modes. So they have different number of higher order modes. Some have like 2, 2, 2, 3, something like
In the GR.
in the GR, but this one is the non-GR
So
one.
non-GR mode is something, theory somebody has proposed according to that.
Yeah, there are many non-GR models, and we have some non-GR templates as well. And for such contradicting events, we sort of test.
So hard is to get this. I mean,
How
the
accurate
non-
is those templates?
yeah, on
Because
yes, but hard
the ring down phase.
Yeah, it is. So, which is why we have multiple approximants. So there is not one approximant which has all the physics encoded in it. So we run multiple parameter estimation runs using multiple waveform families. So this is again why foundation AI can be useful, because you're running this repeatedly for every single waveform approximate. You're running a PE run, and each time it takes I don't know how many days. Which is why it was like it is only being published like a few months ago, but it was it was discovered in 2023. So for 2 years, the collaboration actually analyzed this event, and then in just last month, they published this paper.
And also these are not detected online.
This is detected online as well, and then it was followed up with offline analysis for parameter estimation. But this is a single
No
detector.
counterpart.
No,
Even if it is detected online.
this was actually detected by a single detector. So
cloud signal. Yes, signal to noise 42.
42 in just one detector. The other event, which is of similar nature but 2 detectors, is 250114. This is a more recent event detected in 2025, and this signal is an exact copy of 150914, but it has SNR of 80 or 81. And the only difference, and the reason 1514 had SNR of 24 and this event has SNR of 80 is because the improvement of the detectors. So that is how much the field has progressed since the very first detection. And because it is such a loud event, it was possible to test Hawking's black hole area theorem, which says that the final area after the merger of the remnant black hole will always be greater than equal to the individual areas of the component black holes, and this is the plot that is confirming that.
But here this non-GR thing has not been applied, has not been tested with the.
So for all exceptional events we do test of GR and all the GR tests pass for this one. There is no deviation.
But that 2023 case event.
Yeah.
They have tested with the non-GR case.
They have tested, yeah.
But for this case, why is it because the discrepancy came?
No, there is no discrepancy here. So all,
Only when they find some discrepancy, they try the non-GR test.
yeah.
Chayan, just
Yeah.
one question. So you are saying that the different orders are changing in the first four slot
Mhm.
in the 230814.
Yes.
So is there a measure that if I do higher order, corrections or I include the higher order in the web forms,
Mhm.
is the agreement with GR getting better or worse? I mean, my point is that is it possible to quantify, like, I mean, it's of course possible that how good are the fits when I'm.
You can do it. So
Yeah.
you can do mode by mode computation of the signal
Yeah.
to noise ratio. And so you
Is
may,
it like that if we had higher modes, then it's a better agreement or?
yeah, so for these particular approximates, I think all the modes which were available in this particular waveform model was used in the analysis. And but if you can always simulate a waveform where you know which modes are present, and you can do mode by mode comparison. So you look at the SNR with one mode missing, with and with all modes present, and you can see the difference. So that is how they test these modes. Okay, the next one I'm not going to speak about in a lot of detail because Kostov recently, I think, gave a talk about this event, 23. So it is the most massive binary black hole merger which we have detected so far. And there is a high probability that at least one of them was inside the pair instability supernova mass gap. And there is the reason it's also interesting is because there is a lot of waveform model systematics. So we've been talking a lot about these waveform models, but essentially these are all very approximate models. They do not contain all the physics, and we can see that when we have such a high mass events, all of these waveform approximates really break down. And there is a lot of disagreement. I don't have the plot here, but if you look at the paper, in the appendix, there is one of the figures which shows how different the posteriors can look for individual waveform models for an exceptional event like this, which has very high masses. So, and this is again another event where foundational AI could be useful. So here I'm trying to make the case for foundation AI. First, for searches, we have seen that supervised methods struggle in the presence of glitches and varying power spectral density of the noise. And usually, machine learning models perform well for high chirp masses. And the foundational AI solution is you can have open source audio foundation models, which is already trained on a large corpus of waveforms. So if you use an audio model, which is rising the same frequency band as gravitational waves, as glitches, these models are trained on hours and hours, several thousands of hours of audio data. So they are exposed to much more robust or much more variety of waveforms compared to the gravity spy or other supervised classifiers. So these could be used in a machine learning pipeline to make our searches more sensitive.
You are saying that you are modeling the noise.
Yes. Or we are sort of exploiting the pre-training of these large models to classify the glitches better. Next is parameter estimation. We can see that we have seen that normalizing flows can match the sensitivity of MCMC and nested sampling, but when we have events like 23, because these normalizing flows are also trained on a waveform model, specific waveform model, it will also show these waveform model systematics. Now, with foundation AI, however, if we have this large model, one network which is trained on all waveform models that we have currently, and also numerical relativity simulations, which are not approximate, which are much more accurate than these approximate waveforms, they can probably discount some of the model-specific artifacts, and while simultaneously they can also learn about these glitches. And also, as I mentioned earlier, it can amortize the cost of inference over multiple PE runs. And this is something that I'm working on currently, which is when we have a possible violation of general relativity for 2308 or 2814 like events, it will be very interesting to take a look at what a foundation AI model can generate. If we are able to generate the reconstructed waveform of an event like 23 or 14, we can see whether a model which knows GR waveforms very well, what that model thinks is the right waveform for that event. That will be very interesting to look at what it looks like. And this is something I'm currently working on. Next is detector characterization. So as I mentioned again, like glitches are a big problem for all kinds of classifiers. And the foundation AI solution is, again, if we have a pre-trained model which is exposed to a lot more diverse waveforms, then probably it can give us some advantage over the supervised classifiers, because these other supervised models are only trained to look for what we know or what we have identified as glitches. But there are always new glitches which are coming up in LIGO.
But they should be using from audio foundation model.
Yes,
Means our day-to-day audio.
audio. Yeah.
Then that is a complete different set of data compared to LIGO data. How
Yes.
can you say that
So
there
that
is
is
some
that is what I've worked on, and I'm going to talk about that. So, and I want to mention here that this idea is actually not very new. Foundation models are already being widely used in astronomy. For example, BTS bot is a supernova-based model, and AstroClip is a model for galaxies. So it's a foundation model which is trained on images and spectra of galaxies, and then it was used to estimate photometric redshifts and mapping masses of the galaxy. So yeah, this is being adopted in the wider astronomy community, and I think there is a case for using foundation models in LIGO as well. So the machine learning model landscape, according to me, should move from specific architectures like this, individual models for specific tasks, to general architecture where we have one foundation model which knows gravitational waves trained data, both the waveform, astrophysical waveform, as well as the noise and the glitch. And then we can tune that foundation model for whatever downstream task we care about, like detection, parameter estimation, glitch analysis. And the advantage of doing this is we never have to retrain our own model from scratch again, because we have a model which is robustly trained, and we can use the embedding space that this model has generated, and we can leverage that rich embedding to do whatever task we want, because essentially all we are working with is data that is coming from LIGO. And if we feed that to this foundation model, it should be able to learn everything that we care about. So yeah, so existing pre-trained models would already be near optimal. So with very little fine tuning or almost no fine tuning, we can get very good results out of it. So I talked about LIGO, but the future will have many other gravitational wave detectors, hopefully. So we'll see how that works out. So right now we have 3 to 4 kilometer long detectors detecting BNS up to 180 megaparsec. This is O4. Next we'll have O5, where we'll have 3 to 4 kilometer long LIGO detectors at A+ sensitivities, which is about a factor of 2 better, detecting up to 350 megaparsecs.
Which is the fourth?
LIGO India.
Oh, I was anticipating that it's LIGO India.
Yes.
Anyway.
That is the hope, at least. Next, we'll have A sharp, which is a proposed 2 times improvement over A+ in the sensitivity of LIGO detectors, and whose BNS range will increase up to 600 megaparsecs. And then we'll have next generation detectors, which is beyond 2035, where there are different configurations. So we can have 2 proposed Cosmic Explorer detectors, one 40 kilometer and one 20 kilometer arm, and an Einstein telescope, but it can have either of 2 configurations. Either it can be a triangle with 10 kilometer arms, or 2 15 kilometer long L-shaped arms like the LIGO detectors. So we'll see what we get when we reach there. But we have done some studies about what kind of sources we can detect and what kind of multi-messenger astronomy that we can do using all of these detectors. So the current detection landscape looks like this. So we have until 03, we had 90 confirmed gravitational wave events. In 04, we have 243 significant detections. So this was until this morning. And we have many more low significance detection candidates, which is 4,904. And this is using 2 LIGO sites, Hanford Livingston, and Virgo and Kagra is also operating jointly. Although we've not had many cases within 04 where all 4 detectors were operational at the same time, but still they are running. But when we have other detectors like A sharp and CE or ET, we can see that we'll have millions of binary black holes, binary neutron stars, and neutron star black hole binaries. And as we can see here in this figure, basically all of the neutron stars in the universe up to redshift, this is 10, and all of the binary black holes to redshift similar 8, I guess, can be detected using these advanced instruments. So basically all these new facilities will allow us to see basically all the neutron stars and black hole coalescences in the universe. Now, what kind of multi-messenger astronomy we can do? So this plot shows A sharp, and 1xg, 2xg, 3xg are different numbers of next generation detectors and A sharp detectors. So when you look at these figures, assume that there is next generation plus the LIGO detectors. So we can see here that and this plot compares the 90% credible interval, the area of the 90% credible interval for these events at different signal to noise ratios. So we can see even with A sharp, we probably won't get any BNS with SNR about 100. For that, we need next generation detectors where we can get many events with 90% area less than 10 square degrees using A sharp and next generation detectors. So hopefully we'll get more multi-messenger observations. We haven't had any in O4, which is quite disappointing, but hopefully with next generation detectors, we'll have a few. Yeah.
This one, the left top panel, where
Yes.
it's not getting this detection, but what is the SNR value typically there? 5, 10?
This is 50, so maybe 25.
That's not even that bad, but that's also futuristic prediction.
Yes. A sharp is,
The sharp is the one that you showed.
yeah, so it is going to be 2030s.
Still, we expect at least SNR of 20, I would say 50 events.
Yeah.
50 detections.
Yes. Yes. Now, here is a plot which shows the expected BNS detections per year with these different combinations of future detectors. And what we see here is that for optical counterparts like kilonovae, like which Vera Rubin or Nancy Grace Rubin Space Telescope can probe up to redshift 0.3 to 0.4. So we can see a lot of events using these next generation detectors. So there is a scope to do multi-messenger astronomy using next generation detectors. But for GRBs and afterglows, we can basically probe beyond the peak of star formation using redshift 2. And this includes, so we won't get kilonova, but we can get extremely energetic GRBs and afterglows using these next generation detectors. So what this basically means is that the future is very bright and we'll have lots of data to analyze. And currently we don't have the data analysis infrastructure to deal with all of this millions of data, right? So of course we need foundational AI, and we not only need foundational AI, we need something called multimodal foundational models, which is taking not just input data in one modality like text or video or whatever, but multiple modalities. So I mentioned about AstroClip in the beginning. AstroClip is a multimodal foundation model. It was trained on spectra data and it was trained on images. So you had separate encoders for images and spectra, and then a shared embedding space was generated using these different modalities. And it was this embedding space was tuned using some self-supervised fine tuning. And then with zero shot prediction, which means without any additional training, you could get redshift prediction. And maybe with some nearest neighbors, you could do classification. So yeah, so that was the entire idea of AstroClip, which is a multimodal foundation model for galaxies.
Determination using some photometric.
Yes, so you had images and you had spectra.
No, that's for the training.
Yes, but for prediction as well, you have maybe a candidate galaxy, you have the images and the spectra, and then the model just spits out the.
So I need the spectra to get redshift here.
Yes. At least that's what I remember. I can go back and check.
If I have the spectra,
Yes.
very accurate redshift. So it must be that they are trained with redshift and photometry, and it's actually the photometric catalog from where you are getting the redshift. Because if you have the spectra, then why do you care? Because your spectra will give you
Will give
very,
you-
very accurate.
That is true, yeah.
Yeah, so
Maybe
I
we can fill the
suspect
gap.
that it's just the photometry probably.
Maybe it could also fill the gaps. For example, we have the image, we don't have the spectra, maybe.
That also is possible in
Yeah.
some, but I think it's mostly the
But
photometry.
is it only doing photometric, it does morphological classification?
Yeah, it
No,
does this classification.
Question
I think
is,
it's-
how many images do you need for prediction? Many photometric images will need for
No, I mean, since Chayan was only talking about redshift, that I think you can just
Yeah.
use the multimodal foundation AI things to get it from photometry.
Photometry itself, but it also predicts the masses and as Sir mentioned, the morphology also, the
Of the
classification.
galaxy.
Yes.
Then.
So I am teasing foundation models since the start of the talk, but I haven't really talked about foundation models that much. So how do we actually build a foundation model? And I'm going to very briefly go through this architecture, which is crucial for most foundation models that we have encountered today, which is transformers. So essentially, a transformer consists of two parts, an encoder and a decoder. These are both neural networks, and you can basically have any kind of neural network layers in an encoder or a decoder. But for text-based transformers or for transformers in general, we have some specific architecture, which I'm going to talk about. But essentially, the idea is that you have maybe a text in one language, and the model will output the text in a different language. This is how it was first trained. So first, the input data, which is the sentence "How are you," goes through an embedding network, which generates a high-dimensional vector representation of the input tokens. So every word has a vector representation in this rich embedding space. And then we have positional embeddings, which is encoding information about the position of these tokens in the sentence. So that is the pre-processing part. And next we go into the depth of the architecture. Now, transformers are super powerful, but they're also the simplest algorithms that is in use in computer engineering, because it is just basically a dot product. So you have three matrices: the query, key, and value. The query is one word in your sentence. The key is all other words in your sentence. You basically compute the dot product of the query and the key, and then you output the attention scores. The attention score is basically telling you how relevant a word is compared to others. For example, in this example, the model has determined that R and U are the words which the model needs to pay most attention to. So the higher the attention score, the higher is the importance in the context of the prediction for the model, and the more attention is paid to that part of the sentence. So basically, the entire field of ChatGPT, generative AI, whatever, natural language processing has become revolutionary, all because of this very simple operation. This is called attention. And the other important idea is that you don't compute one dot product, you compute many dot products, which is why you have multi-head attention. So maybe one dot product is looking for verbs, one dot product is looking for the tone of the sentence, one dot product is looking for nouns, something else. So when you do this many times, you get a very, very rich context from which the model can learn and then make predictions. So basically, that's all you need to know about transformers for the context of this talk. Now I'm going to talk about what I have been doing and how I have been playing around with these transformer-based models. So I looked at this audio transformer model called Whisper, which is OpenAI's model, which was trained on 680,000 hours of multilingual and multitask supervised audio data. And Whisper, it was pre-trained on log-mel spectrograms of 30-second audio data at 16,000 Hz sampling rate. So this is going to be important later. I'm going to talk about it in more detail.
So, Chayan,
Yes.
the tea is here.
Oh, okay.
So, no, but that's okay. But do you think 5 minutes?
5 minutes should be fine. Yes. So my question here is, can a foundation model which is extensively trained on human speech be adapted to learn about gravitational waves? And the reason we believe it is interesting is because CVCs lie in the audio frequency range, So how about we use a pre-trained audio transformer to see if it can run about gravitational waves. So the trick that compact binary coalescence. Yeah. So the trick that we use here is parameter efficient fine tuning, which means instead of training all the weights of the neural network, we train only a small fraction of the weights. We usually train 0.5% of the weights of the neural network to make to fine tune it for the task, for the gravitational wave task. So this has become extremely popular within the transformer world. I'm not going into the detail of this. This is basically a particular way of doing parameter efficient fine tuning, but the idea is the same, where we basically decompose the weight matrices into very lower ranks, and we train only these weights and keep the original weights absolutely frozen. So only this weight, which is of lower rank, is tuned on gravitational wave data. The original weights are completely frozen and it still has the data which it has learned from the audio signals. So we can pick OpenAI's Whisper or your favorite pre-trained foundation model, and we can apply these techniques and attach some downstream neural networks for the task that we care about. And we can do detection or we can do posterior estimation for parameter estimation. This is how we fine tune Whisper. And this is how we build GW Whisper, which is basically an adaptation of Whisper or OpenAI's Whisper for gravitational wave detection. And I'm not going into the details of this, but we basically made a lot of domain-specific adjustments because Whisper, as I mentioned earlier, was pre-trained on log-mel spectrograms with 30-second input at 16,000 Hz sampling rate. All of this is not essential for gravitational waves because these signals are extremely small, and the sampling rate is usually typically 2048 Hz, not 16,000. So we made a lot of modifications in the architecture before we applied it. And we tested on the mock data challenge that I mentioned earlier. This is GW Whisper's performance compared to the other pipelines. And what we found is that although it is not up to the same sensitivity as match filtering or some other machine learning pipelines, it is giving us better sensitivity at false alarm rate of 1 per month compared to 2 other machine learning models, which is not great, but also for a model which is only trained on audio data, it is pretty interesting. And we want to push the limits further and see what modifications we can make to improve it. There is one critical limitation, which is GW Whisper is trained on spectrograms, and spectrograms usually they lose some SNR. So already we are only more sensitive to higher SNR samples compared to lower SNR. So that is one critical limitation in the approach, but we are building towards that. And we ran GW Whisper on the second half of O3B data, and we discovered 18 out of 31 confident BBH events using our model. And out of those 18, 15 were detected at a false alarm rate of 1 per month, which is basically the threshold for online detection. Next, as SSR asked, so how can we we use audio transformers for glitch classification? So basically, we found that without doing any modifications, without doing any domain-specific modifications, if we run the model through some glitch data, we get really good classifications for glitches. So this is a confusion matrix, and we can see that the diagonal is dark, which means all the different classes of glitches have been classified accurately. And the numbers are not really visible, but they're all greater than 0.9 or 0.91, which means they're classified correctly with greater than 90% accuracy for all classes. So this is without doing any gravitational wave modification, gravitational wave specific modifications in the architecture of the model. We can see that it is very robust and can identify glitches better than models which are trained specifically for glitches.
I understand that you can classify glitches,
Yeah.
but our task was to not classify,
But to remove
or detect the glitches, right?
Right. So this is the first step. Here we have detected the glitch. Now, in terms of actually modeling the glitch, that is something which is the next step. So we need a way to modify or model the glitch itself and then remove it.
Now, are we detecting 100% of the glitches, whatever present there in this model, or not?
We are detecting like the classification accuracy is greater than 90% for all types of glitches that we have considered so far. All right. So what the lesson that we have learned from our experiments with GW Whisper is that these pre-trained audio foundation models are useful for certain tasks, but maybe we need to build a foundation model from scratch because at the end of the day, these are audio models. They are not sensitive for gravitational waves. So how about we just train a model from scratch which is meant for gravitational waves? Right. So I've been doing some work on that. I'm not going into the details of it, but as I was talking about, the way to model the glitches is to do a reconstruction of the glitch waveform from the noisy strain data. So we are working on that, but right now we have done a reconstruction of gravitational wave signals from using a neural network model called AWARE, or Attention Boosted Waveform Reconstruction Network. And this is the result for GW231123. So we can see here that the strain data, which is shown in gray, and the neural network performance matches with the reconstruction models, which are non-machine learning based. And we get a 97% match with these other pipelines, which are either model based or model agnostic approaches. And we can see that if we expose the neural network to data which it has not seen, like higher masses and mass ratios, although the model has never seen such data, it can still reconstruct these waveforms pretty accurately, which is basically the power of these foundation models, that it can generalize to new domains. Same goes with eccentricity. If you have eccentric binaries, the model can, although it was not trained on eccentric binaries, it can still reconstruct eccentric waveforms. Also, higher order modes. So if we increase higher order mode content, we can see that the reconstruction accuracy is consistent. So this on the y-axis, we have the SNR of the reconstructed waveform versus the actual SNR, and they peak at 1 for all kinds of higher order mode content in the waveform, which shows that no matter what higher order mode you have, the model is very sensitive. So I'll skip this slide for the sake of time, and I'll leave with the conclusion. So foundation models are important, and I believe that we should put more effort towards them. And with GW Whisper, we were able to show that some pre-trained models are already useful, but maybe a model which is trained from scratch specifically for gravitationals could be more useful. So thank you.
Okay, questions?
I asked a lot of questions.
Yes, Anirudh?
Fantastic talk, Chananda. But I have a kind of a vague question. I don't know if it makes sense. So, since these are all task agnostic models, so I've heard around that these sort of models usually hallucinate a lot because they're not trained on specific things to look for.
Yeah.
And then they also become biased. For example, if you're training your model on audio signals and you're looking for gravitational signals, so it could be biased towards the signals that are glitches that occur more in audio signals than so.
Absolutely. So, which is why what we have found in this work is that GW Whisper performed much better for glitches than signal detection because it was never exposed to gravitational wave data. It did well, but it could have done better compared to models which were trained from scratch. Which is why I had a slide which mentioned that these are useful, like pre-trained architectures are useful for certain tasks, but if we really want to have a foundation model for gravitational waves, we should build one from scratch. So not even AstroClip. For example, AstroClip was trained on a lot of images, but not galaxy spectra, right? So even AstroClip has some problems. So if we really want to exploit the full potential of a transformer, of a foundation model based on transformers, we should train it only on the data that we are working with.
So again, coming to this question, actually. So what parameter does it use to identify that this is a B?
Okay, got your question now. So the gravity spy I mentioned, which is the CNN classifier, it has already classified those glitches.
No, I'm talking about that
Yeah.
AI foundation.
Yes. So